Hello, and thank you for listening to this short presentation. Today, I'm going to discuss optical spectroscopy for the nanoworld, and in particular, an analytical technique called cathodoluminescence. Many of you will be aware that there is a fundamental limit to the spatial resolution of optical microscopies and spectroscopies due to effects of diffraction. In a perfect optical system, that resolution limit is about half the wavelength of the light used in the illumination. So in the best case of blue light, around 200 nanometers. However, many important optical technologies, such as nanophotonic devices or semiconductor nanostructures, rely on particles or have features which are much smaller than the diffraction limit of light. The examples shown here are nanoantennae. They're formed of gold, palladium nanostars, and they're less than 100 nanometers in size. Consequently, optical microscopies and spectroscopies have insufficient spatial resolution to interrogate these nano-world objects. So I'd like to introduce you to a technique termed cathodoluminescence. Cathodoluminescence is the emission of photons from a material when excited by an electron beam. In an electron microscope, we can focus an electron probe to sizes and use this to excite a specimen. And by measuring the emitted light using a cathodoluminescence detector like the Monarch system, we gather optical information far below the diffraction limit, since the electron beam and its interaction with the specimen determines the resolution, not the optical diffraction limit. As you can see in this example, we can analyze the optical emissions of individual nanostructures and demonstrate a spatial resolution clearly better than 20 nanometers. The information contained in this cathodoluminescence map on the right-hand side reveals the spatial distribution of the photon emission probability, the wavelength distribution, and polarization state of the light that's emitted, but it could also include emission direction too. Previously, such data could only be gathered in what I term a hero experiment, where an expert user spent half a day adjusting everything just right, and if they performed the complicated setup and alignments perfectly, and luck is with them, they may be able to obtain some sort of results. However, the high-quality data shown here was captured by a user with less than an hour's experience using the tool and took just 120 seconds to collect. They were using the brand new Monarch detector. The unprecedented sensitivity and automated alignment routines of this system really redefine what's possible in cathodoluminescence microscopy. It enables novice users to capture hero quality data. So having the ability to routinely study optical properties at deep sub-wavelength resolution really opens the door to answering a wide range of important questions. From basic science problems such as how light and matter interact at the nanoscale, revealing, for example, the local density of optical states or performing energy momentum spectroscopy in nanophotonic systems or photonic crystals, to industrial solutions such as failure analysis of LED devices and displays. The ability to capture optical information across the macro, micro, and nano worlds and directly correlate that with physical properties, and including composition and chemistry, makes cathodoluminescence an impressively powerful tool. If you'd like to learn more, come and explore whatiscl.info. It's an educational website where you can discover what cathodoluminescence microscopy and the Monarch system can do for you. Thank you for your time today.